Okay, thank you. It's really an honor to give the talk here, especially after this very impressive talk by Dr. Ho. But I would like to switch the field a little bit. And since we're theoreticians, I'll be talking about our computational studies of nanomaterials introduction. So the talk would be a little bit more about the property of materials and the property of some interesting phenomena. Okay, and so I guess both of us are condensed matter physicists. We work with interesting materials. Be that molecules on the surfaces or some nanomaterials on the surfaces. And nowadays, physics and chemistry is really kind of intertwined together, because in this institute we have physical chemistry and chemical physics here under the same roof. Okay? And in studying materials, we are mostly interested in those possible applications, and so we kind of choose the materials carefully, and then and try to see that's what we could do to solve some of the emerging problems that will be challenging all of us. Okay? And so the topics I'm going to talk about today would be two-dimensional materials, which are new, because there will be some properties that are not seen in the book. Okay? And by two dimension, I mean that those will be some materials that are only a few atomic layers thick, so that we would not have the periodicity along the third dimension. Okay? And so we have already heard a lot of exciting news, exciting discoveries in this field. And today I would like to mention a bit how computational studies help us our understanding of those materials. Okay? So we have already seen in the previous talk that whatever the experimentalists see in the measurements, we need to have some explanations. And so a couple of years ago, this is in the United States, and the government launched this materials genome initiative. Okay? And it was recognized that to develop advanced materials, this development can be accelerated to the use of computational capacities in an integrated approach. Okay? But fortunately, we do not have to spend so many years to build our own supercomputers. Okay? So we could just use the facilities and then try to focus on the system. Okay? So I know that there are people in the audience with various backgrounds, so let me just say probably just a few slides to introduce the methods and how we should look at that. Okay? So in physics, the interaction in condensed matter, and in terms of fundamental physics, we know what the interactions would be. And then the challenging is that we would like to predict materials properties from microscopic quantum theory. So we're going to have those atoms, and we have those ionic cores, and then electron cloud will be around those cores. And then we all know that this is a very, very challenging problem because we have to talk about interacting electrons, a lot of them, even we know the Hamiltonian. Okay? To some physicists, if we know the Hamiltonian, the problem is solved. But for us, we really want to get some numerical answers out of this equation. And then, of course, electrons are fermions, so there are even more challenging problems that we need to talk about electron correlation there. Okay? And so nowadays, the development of the whole theoretical approach has been able to tell us the differences between different elements and different atomic configurations. And for instance, the difference between aluminum and silicon, the number of electrons, you can change that number by 1, and you're going to get all different physical properties there. Okay? So in the so-called first principle studies, what we want to do is that we would want to use whatever we have learned, have developed, and try to answer those questions about the basic properties of those materials. Okay? And the standard model nowadays, we just need to use atomic number and arrangements. We have all sorts of approaches, methods, especially density functional theory for the ground state. It may be a little bit money-buddy approach if we have strongly correlated materials. And by looking at the density only, that would simplify the calculation tremendously because densities will be scalar functions instead of going to the full wave function that will have all the phases. Okay? And so we could study ground state properties, excited state properties, and then those calculations could also provide input parameters for various model studies. Okay, I think this would be the only introduction I'm going to give. If anybody's interested, and we could have more discussions about the details of the calculations. Okay. All right, so the outline of this talk, I would like to discuss some of the 2D materials. Of course, we all heard about the story of graphene. And then I would focus on particularly some recent work we have done and to answer the question, what is 1 plus 1? So we put 2 together. Okay? And graphene, bilayer graphene, and also other 2-dimensional materials, and like a transition metal that called calcinides. And so we'll be talking about looking at some of the effects of the stacking patterns. And then if I have time, probably won't have time at the end, to talk about some interesting properties of different instability or different competition of different ground states. Okay. All right, so graphene, I guess everybody has seen 2-dimensional materials, and then the property have been studied a long time ago, and many years ago, people have already recognized that near the Fermi level, so this is the energy versus the wave vector of the electron in the solid, and this 0 means that Fermi level. Below that level, everything is occupied. Above that, everything is empty. And the energy dispersion, okay, near the Fermi level is very special because that's going to be linear with the momentum k, which is very different to what we have understand what happens in the solids. Okay? And so this famous direct cone, okay, it goes in any direction. We have that linear dispersion. So all these physics that have been studied in the past 10 years or so focuses on the very special property of graphene that was predicted more than 30 years ago. And that is that if we go to the low temperature, low energy properties of electrons, those low energy electron dynamics could be described by this famous direct Weil Hamiltonian, where so the detailed thing I probably want is like the Hamiltonian describes the neutrinos, and then energy will be proportional to the wave vector. Okay. All right, so so in the past few years, or maybe there are a lot of studies for those kind of relativistic physics in a non-relativistic material, just because of the similarity in the Hamiltonian. Okay. All right, so after that, so that's a single layer 2-dimensional materials. Okay. More recently, people have focused on some kind of artificial structure, because once we have those 2-dimensional materials, we could pack them, okay, in various ways, and then look at the properties. And so this is a perspective. So the interaction between those layers through van der Waals interactions. Okay. Van der Waals interactions would be very interesting because it's weak, but on the other hand, it would change the features of the system to a certain extent, and sometimes it's kind of surprising. Okay? So in this discussion, and we have been thinking about, and people in this field, that we would have a way to stack them together And just like you're going to build up something with Legos. Okay? All right, so depending how you pack them, and you may be able to get different properties for the final structure. Okay. All right, so when we pack those graphene layers together, okay, so this is from experiments, HPN images, okay, and when you grow them, once you reach the multi-layer regime, and they're depending on the growth condition, or you could take one layer and you put on top of the other, you may not be able to align those two layers perfectly. So in the experiments, there's a rotational angle between those two layers, and you're going to see this kind of moire pattern. Okay? And so that would give us something quite interesting, because this is not something you're going to discover in nature. Okay? So this kind of artificial structure. Okay? And so for this specific example, it's twisted bilayer graphene, and it's somehow coupled with direct fermions. Okay? So that would give us another incandescent matter, another system. We could study those coupling between these massless particles. Okay? All right, so if I look at this, so this is a picture with about 5-degree rotations, and those moire patterns, we zoom in, we look at from a distance, you see that just because of the local arrangements of these atoms for those two layers, and you're going to see some kind of moire pattern, some kind of periodicity. And if they zoom in, there are areas that would be, we call that AA region, because if you enlarge that, you will see that the atoms will be, the top layer will be right on top of the bottom layer. And the other region we call AB region, because that would be, they will kind of separated to see them. Okay, so in this situation, we have a system that the stacking pattern change as a function of position, which that means you could kind of look at the combined properties, or you could look at some kind of local properties. And they all happen in one sample. And at the same time, we have some kind of moire pattern, which is the size is going to be much larger than the chemical bonds. So you introduce some kind of artificial periodicity into the system. Okay, so those will be the two key factors, but they're going to give us very interesting properties for the materials. Okay, so for this system, we have done a series of studies. I'm not going to be talking about all of them. Okay, so there are some interesting things about the anisotropic transport in terms of energy range, and we're going to observe some kind of coupled direct fermions, and we have some kind of neutrino-like oscillations. Okay, but I was going to mention this fractal like energy spectrum on the magnetic field a little bit. Okay. All right, so what we could do is, of course, set up the calculation on the computer, and then try to get the behavior. Okay, so for instance, if we're going to rotate the layers in the real space, and we're going to have those directly rotated in the momentum space also. Okay, so we have one cone from one layer, then the other one, the right one from another layer. If there's no interaction, you're going to see two of them, but with interaction, we're going to see that some gaps will be opened, and then the balance dispersion will be changed. Okay, and there could be more complicated changes in other cutting, or so that's. But just the real calculation we could do is put in this everything, and then we really see that this schematic thing will be correct, and it turns out that this is a saddle point. This 2-dimension, in which it will have a very high density of states, and this could be verified by experiment. Again, this is STM. EIDV means that it's a first derivative. We measure the density of states as a function of bias, and we see the peaks in the density of states, and that would indicate that the energy bands, okay, really follows this kind of picture like that, because otherwise you will not see those peaks in the density of states in the experiments. Okay, so in this field, we work closely with experiments and then try to figure out what would be the new features in the system. Okay. Another example is the electrons in a magnetic field. Okay. Two-dimensional electrons in magnetic field. If you have taken any kind of solid-state physics or quantum physics courses, and you will know that the cyclotron motion of electrons will be quantized. And we're going to have so-called the Landau levels. So in the usual two-dimensional electrons, energy goes like a k-square, and the magnetic field, energy versus magnetic field will be like that. It's linear in the magnetic field. But if we have a dispersion linear in K, and you do the calculation, and your Landau level would be proportional to the square root of the magnetic field. Okay. All right. So this is a proof that we do have this kind of a linear dispersion. And then if we just look at the energy scale for 1 Tesla, and the separation of the levels will be 40 millielectron volt. That means you could do the experiments at room temperature in this system versus in the traditional two-dimensional electron gas measurements. If you want to separate the Landau level, you really have to go down to very, very low temperature because this energy scale, the separations are for the order of 0.1 millielectron volt. Okay. All right. So this is the usual thing you're going to see in the textbook. Okay. And but the question is that this is really a calculation without any lattice. We don't have any periodicity in the system. Okay. So if we put in the lattice, some kind of periodic potential, this is a famous problem in mathematical physics. Then was done was reported 40 years ago. Okay. So what this says that if you put in the periodicity, then we're going to have two competing coexisting length scales here. One is the magnetic length, that's the radius of the cyclotron motion, roughly. And then also you have a lattice constant. Okay, so the electron will have to kind of balance these two length scale, and then the energy versus magnetic field will show very complicated kind of fractal-like picture. So this is a very real situation. In quantum mechanics, you're going to see those kind of self-similar fractal-like structure, except that the horizontal axis we're seeing here, energy versus magnetic field, this is plotted in terms of the magnetic flux over the flux quantum. Okay? So the flux is going to be the magnetic field multiplied. This is a 1 unit cell area like that. Okay? So this is from the calculation, and but it has never been observed in the real system because this unit cell is of the order of a few angstroms squared. Okay, so that means that this ratio is going to be very, very small, and we don't have a big unit cell in order to see the details there. Okay. And so it has been a very interesting problem for mathematical physics because this energy gap are labeled with parameters related to the topological numbers, term numbers. And then in recent experiments for those ultra-cold atoms, they could put things on the lattice, and they're trying to generate or measure this kind of spectrum. Okay. All right. So for graphene, okay, if you put in the honeycomb lattice, and you do the calculation, okay, and then so what happens is even if you have a very, very large magnetic field you achieve nowadays, for instance 40 Tesla, this ratio is going to be 10 to the minus 3. So that means we'll be looking at something only in this range, okay? And that's why we're going to have this Landau levels proportional to the square root of B, okay? And we would not be able to probe anything here because we don't have that kind of big magnetic field we could generate. and to study really the detailed things about this fine structure, the topological properties, and things like that. Okay. However, if you go to this twisted bilayer graphene, experimentally, it will generate a small ray pattern, and depending on the different angles you have, the size of the moire pattern increases when the angle decreases. So we could probably reach like a 10 nanometers at the range about 1.47 degrees. Okay, so this is much, much larger than the unit cell of the graphene lattice. Okay, so we can do the calculation. I'm going to talk about the calculation, how you do that, but to calculate this energy spectrum as a function of magnetic field, I'm plotting that in terms of the absolute value. So for different angles, the theory could predict that you're going to see those fractal-like energy spectra. If you zoom in, there are different gaps there, and then the bilayer system is a little bit different than the one layer because you're going to have the coupled direct fermion, so this variation will be different from the single layer calculation. So this would be, if you go to the right angles, you will be able to detect those very complicated structure in the experiment doing by STS or something. Okay, so that would provide some vehicle for us to study some of the physics that has never been have never been able to study in the past. Okay. All right, so that's for the graphene. Okay. Now, other two-dimensional structures. Okay. Nowadays, those TMDs. Okay. And so when we want to build some heterostructures, we have to stack them together again. Okay. And so this is a layered compound in the bulk. Okay, so nowadays, once we have the ability to do the measurements for those single atomic layers or multiple atomic layers, and we've been able to grow them in the laboratory using different methods, and then so we would make this. So this is a single layer. It's really, we have 3 atomic layers, so it's a little bit complicated. And so this is a compound, so you got a metal atom here, hydrogen atoms in another layer. So you'll be able to stack them together and then see whether you could get some new properties or change the properties of this in the bulk. Okay. Again, if we want to build those heterostructures, the stacking is always an issue. And as we see that, I mean, the Lego picture is the ideal one. When you put 2 layers together, they don't want to be in registry. Okay? And we have atoms, we have this lattice in those layers, and then we have to consider lattice mismatch problems, and then this is really not a uniform bilayers or tri-layers. And so this will be something that's we could probably understand first from the theory. Okay, now if you stack them together. Okay, so this is a complicated view graph, so I probably don't need to look at the details. But so for instance, we take 2 TMDs and put them on top of each other, either by growth or by just place 1 layer on top, and they have a 5% lattice mismatch. Okay. So even if you line them up, so this is 0-degree rotation, and then you look down, then you're going to see that there are different regions. Okay. Now they're color-coded, so there are different ways to classify them. But if you don't just look at the different areas, you're going to have a different arrangement. And then, so this gives us a very convenient playground, because those stacking patterns will not be obtained naturally when we have those layer compounds. Okay? So we will be able to look at what's going to happen in there. Okay? So this is for just lattice mismatch. And if we have lattice match for different compounds, you have the same chalcogen atoms, lattice will match, but if there's a rotational angle, we're going to still see those different stacking regions there. And with lattice match and rotation together, And then we can see that if some angle is big, then the region gets a little bit smaller, then they may not have their own features there. Okay. All right, so what's going to happen for those different regions there? Okay, so this is just a little label. I mean, don't worry about the details because we could identify this is just geometry. Okay, any undergraduate student could do that, put that together, and look at the packing order. Okay, then we put in the packing orders and try to calculate what would be the energy gaps, the valence band and the convection band. And we have a region which is large enough so that the local picture could be measured by local probes like STM or scanning tunneling spectroscopy there. Okay? So with the interlayer separation, it's going to have a variation about 0.5 or so angstrom. So the whole thing will be buckled. Once that happens, the local band gap is going to vary by the order of a few tenths of an eV. Okay? So that means that if we try to build those van der Waals heterostructure, okay, if it's not one system, and one may have locally various distributions, and that probably will give us some interesting transport properties or something to look at. And that would also affect the optical properties locally. Okay, so that would give us some nice feature that we could explore. Okay, and another issue is those are transition metals that combinize, and if we put in different transition metals, then we have a different number of d electrons. Okay, then the Fermi level, the occupied states, will be able to cut to different d orbitals. And we were talking about molybdenum sulfide, which will be this in this group. And then we know we go to other groups, we may get a metals, and then and go to another transition metal group, and we have a different features. So this is a review article that lists all the different properties there. We could go from semiconducting, we could go then metals. And the interesting here is that this is also a prototypical system that was studied, so-called the charge density waves. I can talk about that a little bit. And also superconducting. Okay? So those are all the properties people know previously in the book. Okay? Now we have the chance, the opportunity to grow one single monolayer or two layers and stack them up to build from those multiple layers and then look at their properties in this different limits. Okay. All right. So one interesting aspect is, again, this is physics, so-called the charge density waves for the normally in the layered compounds, and actually we know that all the crystal must be periodic, but for those systems, the ground state, that is, go to low temperature, you're going to see spontaneous distortion for the lattice and the modulation of the electron density. Okay, so it's a kind of a very unique system, and then there are all sorts of proposals in the literature about the mechanism, why this would happen. Okay. And so I will not go into the details, but for physicists, this is a very exciting playground to test all the theories and to see whether you could reproduce what has observed in the experiments. Okay? And so those are some of the current projects we're working on. Again, if anybody's interested, I'll be more than happy to have more discussion, but I will not go into the details. There are different charge density waves for this is for different groups of transition metals, okay? And there are differences in the layers, so there are kind of a three-dimensional variation. And when we go to the single layer or multi-layer, and this whole crossover from the bulk to the monolayer will be of interest, okay? And also in those two-dimension systems, we have the way to add charge carriers by gating in the experiment. So you could put the charge into the system, and then so typical situation is that so this is by doping, but one could see that there are different competing phases: charge density wave and superconducting phase. Okay, so we're always going to see the competition between superconductivity and the charge density waves, even nowadays for high TC materials, and that's also something under intensive investigation about the charge density fluctuations near the superconducting phase. Okay, so we'll be talking about strong electron-phonon coupling there and superconductivity in competition with those charge density waves. So this is something that we are also studying nowadays. Okay, and I kind of went through this quickly because I know that time is short. So I'll leave all the details and for future discussion, I just want to thank the group members, students, and postdocs. They have worked on those two-dimensional systems, and my group here, this is a nice setup right outside this building. Okay, all right, so I think I'll stop here and bring everything back on time, and thank you very much for your attention.